Optical fibers. The optical fibers is consisting of core, cladding, and polyurethane jacket. And optical fiber is used to transmit the light from one end to other end, and covering a very long distances through the bundle of thin fibers. Construction of optical fibers. The optical fiber is mainly consisting of the central part core and surrounded by cladding, and that is covered by polyurethane jacket. And propagation mechanism of optical fiber. The optical fiber which will be propagated through it by the phenomenon of total internal reflection as shown in the diagram. The incident ray incident on the core part, and it is reflected back to core part, and it is a continuous process, and it is not emerging out of the optical fiber and reaching to the other end. And at any instant of time it will be in the core part. The reflected light will have total internal reflections throughout the length of the optical fiber and reaches to other end. The loss of energy through the optical fiber is very less compared to any mechanism of transmission through that much of distance. Then angle of acceptance, numerical aperture of an optical fiber are condition for propagation in an optical fiber. And a diagrammatic representation of the optical fiber, and consider the angle theta naught is called waveguide acceptance or angle, and sin theta naught is called numerical aperture of optical fiber. Let n naught, n1 and n2 be the refractive indices of surrounding media, core, cladding of the optical fiber respectively. Let OA be be the incident ray. At point A, angle of incidence is equal to theta naught. From Snell's law, n naught sin theta naught is equal to n1 sin theta 1, where angle of refraction is theta 1. Sin theta naught is equal to n1 by n naught into sin theta 1. Sin theta naught is equal to n1 by n naught into root of 1 minus cos square theta. Then that is equation number 1. At a point B, angle of incidence is 90 minus theta 1, angle of refraction is 90 degree. Therefore, at a point B, AB is the incident ray, angle of incidence is 90 minus theta 1, angle of refraction is 90. From Snell's law, n1 into sine of 90 minus theta 1 is equal to n2 into sine 90, n1 into cos theta 1 is equal to n2, cos theta 1 is equal to n2 by n1, that is equation number 2. Substituting equation number 2 in equation number 1, we get sine theta naught is equal to n1 by n naught into root of 1 minus n2 square by n1 square. Then n1 by n naught into root of n1 square minus n2 square divided by n1 square. Then that is equal to n1 by n naught into n square root of n1 square minus n2 square divided by n1. n1 get cancelled. Sin theta naught is equal to root of n1 square minus n2 square divided by n naught. That is equation number 3. Numerical aperture. Then numerical aperture is equal to sin theta naught. Therefore, sin theta naught is there, then numerical aperture is equal to root of n1 square minus n2 square divided by n naught. It is equation number 4. Then if the optical fiber is placed in an air medium, then n naught is equal to 1. Numerical aperture can be written as root of n1 square minus n2 square. That is equation number 5. Let theta I be the angle of incidence of radiation of the ray will be able to propagate. Sin theta I is equal to theta naught is less than theta naught. Sin theta I is less than sin theta naught. Sin theta I is less than root of n1 square minus n2 square divided by n naught. Then sin theta I is less than numerical aperture. This is the condition for propagation through the optical fiber. Then next comes out to be fractional index change. It is denoted by delta. Then it is the ratio of refractive index between the core and cladding to the refractive index of core in the optical fiber, and it is represented as delta is equal to delta is equal to n1 minus n2 divided by n1, V number, the number of modes of propagation in the propagation of the optical fiber. V number is given by pi d divided by lambda into root of n1 square minus n2 square divided by n naught. And pi d divided by lambda into n into a, which is numerical aperture. Phi d divided by lambda is into sine theta naught. The light that enters the core within the wave guide acceptance angle, only the light waves in terms of certain number of modes will be sustained for the propagation in the optical fiber. The single ray propagation is shown in the single mode optical fiber. And modes of propagation, is nearly equal to v square divided by 2. V is the V number. That expression can be obtained by using this expression, where d is the diameter of the core, lambda is the wavelength of the laser. Then types of optical fiber: single mode optical fiber, step index multimode optical fiber, gradient index multimode optical fiber. First one, single mode optical fiber. The diagrammatic representation of single mode optical fiber, it is a geometry of the optical fiber. This is the refractive index profile, and this is the ray propagation through the optical fiber. And this is the second one, step index mode optical fiber. This is the geometry of the optical fiber, and it is a refractive index profile, and it is the propagation through the optical fiber. And it is the third one, the geometry of the optical fiber, and the refractive index profile, and ray propagation through the optical fiber. Then single mode optical fiber. In the single mode optical fiber, it consisting of the diameter of the core, it is 8 to 10 micrometer, and diameter of the cladding is about 60 to 70 micrometer. And the refractive index of the optical fiber with respect to the radial distance, if it is plotted, and the refractive index of the optical fiber, it is remains constant here from starting point of the radial distance, and suddenly it will increase at the interface of cladding to core, and it reaches a maximum value, and it remains constant in the region of core, and suddenly it will be decrease where it is the interface of core to cladding, where there is a decrease in refractive index, and finally reaches to the constant value that comes out to be in the cladding part of the region, and it remains constant throughout the cladding region. And here the incident ray of light, when it incident on the core part, the total internal reflection takes place inside the optical fiber and reaching to the other end. The important thing, because the core part is having a diameter of 8 to 10 micrometer, therefore it will allow only one ray to propagate through the optical fiber. Then this is most of the cases in single mode optical fiber are most extensively used in submarines and cable systems, and all aeroplanes, these are used. And about manufacturing of optical fiber, 80% of the all fibers that are manufactured in the world today, they are the single mode optical fiber. The second one, step index multimode optical fiber. As we know, the geometry of the optical fiber, it is the core part will have a diameter of about 50 micrometer to 200 micrometer. Cladding part will be having 100 to 250 micrometer. Then this is about the step index optical fiber. Then variation of refractive index with respect to core, it allows the more number of modes of propagation to the optical fiber, and it will be allowing more number of ray to propagate through the optical fiber. And graded index multimode optical fiber, and core part is not having a constant value of the refractive index in graded index multimode optical fiber. There is a variation of refractive index with respect to core part, and at the center it is radially decreasing order, and finally it reaches to the value of the cladding. Therefore the graded index will have the refractive index profile as go on increases with the center, and it will go on decreases, because the refractive index at the center of the core is maximum, radially it will go on decrease. And ray propagation in this case, it allows more number of ray to propagate because modes of propagation is depending on the diameter of the core, but this ray is not having sharp edges, and it will be having a curve wave guide type, and it will be allowing more number of propagation through the optical fiber. And attenuation, it is the loss of optical fiber or the loss of power of the optical signals against the optical fiber. And there are three types of optical losses through the optical fiber. One, absorption loss, and second one, scattering loss, then third one is radiation loss. First one, absorption loss. There are two types of absorption losses. One is extrinsic absorption, second one is intrinsic absorption. The extrinsic absorption are possible in case of the types of extrinsic absorptions: iron, cobalt, nickel, hydroxy molecules. During the propagation, the signal when photons interact with these impurities, then electrons present in the impurity absorbs the photon and get excited to higher energy state, and they give up this absorbed energy either in the form of heat or light, which has a different wavelength. Intrinsic absorption, the fiber itself has a tendency to absorb the signals of a certain wavelength. Then scattering loss, and here the relay scattering, in the optical fiber there are small air bubbles are introduced while manufacturing the optical fiber that are known as scattering centers. Then whenever a photon incident on these scattering centers, the scattered light will be scattered in different direction as that of the propagation through the optical fiber, and this corresponds to a loss, and this loss is mainly depends on the wavelength of incident radiation. Relay scattering is inversely proportional to fourth power of wavelength. And radiation loss, the radiation loss or bending loss, it can be having two types. Then one, microscopic bending, another one is a macroscopic bending. And this diagrammatic representation shows you macroscopic bending, and this diagrammatic representation shows you microscopic bending. And in the macroscopic bending, the optical fiber bends much larger compared to the fiber diameter. Signal get escape. The loss will be negligible for small bends but increase rapidly until the bending reaches the threshold value. Any bent radius is equal to the threshold makes the losses suddenly becomes large. A microscopic bend. During the manufacturing itself, the fiber will have a defect. This type of loss occurs at core and cladding interfaces of non-linearity is called microscopic bending. The microscopic bending curve irregular reflection from the cladding interface, so after covering a certain distance, some signal get leaked through the optical fiber and leads to fiber loss. Attenuation can be written with the expression lambda alpha is equal to minus of 10 divided by L into log of P out by P in, and the unit of attenuation coefficient is dB by kilometer, where P out is output power in terms of watts, P input is input power in terms of watts. Attenuation coefficient is measured in terms of dB by decibel per kilometer. Length of the optical fiber is measured in terms of kilometer. And point to point communication using optical fibers. And here the voice, transducer, coder, transmitter, optical fiber, photodetector, decoder, transmitter, and voice. And voice, when you speak in the microphone of in one end, the non-electrical signals, that is voice sound waves, are converted into the electrical signals by transducers. The electrical signals that are converted by coder, and it will be converted into binary signals. These binary signals are transmitted through the optical fiber as a light, and the optical fiber, through the optical fiber the light signals are propagating, and other end of the optical fiber the photo detector is kept, and this light when it is detected by the photo detector, it converts light signals or optical signals into binary signals, and these binary signals are converted into decoder by decoder. The decoder converts binary signals into electrical signals. These electrical signals are converted by transducer. This transducer converts electrical signals into the non-electrical signals. Again it will be to the receiver end, and this is the mechanism by virtue of which the point to point communication is possible using optical fiber.